Alright, it looks like we are live. So this is going to be my first live stream as noted in the description. And yeah, I was originally planning to just record a bunch of long videos, but I figured why not? Let's give live streaming a whirl and just figure out how it all works. I won't be too surprised if I end up being, all by my lonesome doing this, but it's whatever. It's for the experience. So for today, my original plan was to pick out specific problems, but I didn't end up having the time to do that, so I just listed a bunch of topics that I think are worth going over, and yeah, let's begin. So the first thing I have lined up is a review of the chain rule. We're not going to do the most basic problems, but I just want to pick out a few problems from here that are fairly challenging. They combine the chain rule with product and quotient rule sometimes, or might be nested chain rules. So let's see, what might be a good one worth picking? How about we've got a function here, f of v equals, where did it go? I already lost it. Equals v over v cubed plus 1, all raised to the 6th power. Okay, so this is going to be a quotient rule within a chain rule. First part for differentiating this to get f prime of v, we are going to treat this like the same way we would treat x to the 6th, so 6 times, I don't think you guys need me explaining this to you at this point. With 1 week left before the AP exam, if you don't know how the chain rule works, then you're probably in more trouble than I had anticipated. But anyway, so 6, all that stuff to the 5th, times the derivative of v over v cubed plus 1. So this is going to be a quotient rule. Let's see, I'll start with the bottom part first. So it's always over g squared, and then it's f prime g minus g prime f. So f prime, derivative of v is 1, times g, which is v cubed plus 1, minus g prime f. So derivative of v cubed plus 1, 3v squared, times f, which is v. And I suppose we could simplify that a little bit. Yeah, let's go ahead and go for it. Let's see, so we've got v cubed plus 1 minus 3v cubed. V cubed minus 3v cubed is negative 2. V cubed plus 1 over v cubed plus 1 quantity squared, and there we go, that takes care of that one. What else do we have here? Here's one that shouldn't be too troublesome, but it can throw you off a little bit if you lose track of which level you're differentiating at. So they say y equals sine of sine of sine of x. So what I like to do for a problem like this is, first of all, make the parentheses less disorienting by using brackets, alternating between parentheses and brackets. So first thing I'm going to do is rewrite this as y equals sine of, parentheses, sine, and then I'm going to use square brackets here, sine of x. And that's just to make it easier to visually keep track of what we're doing and where we're going. Okay, so differentiating, we would get y prime equals, differentiate the outer function first, so derivative of sine is cosine of, rewrite the inside, sine of x, times the derivative at the next layer in, so now we're over here, differentiating sine of x gives us cosine of sine of x times the derivative of the next layer in, so that's going to be times derivative of sine of x, which is cosine of x. So really the only challenge with this one is staying organized and not letting yourself get disoriented. Okay. This one might be slightly more disorienting. Let me switch to a new sheet of paper. So this next one says y equals square root of x plus square root of x plus square root of x. And we want to take its derivative, so y prime will be... Actually, I should probably write it down here because I get the feeling this one's going to be a long one. Y prime is... Well, actually I should start by rewriting this. Yeah, let's rewrite this. Y equals... so all that stuff to the 1/2. We've got x plus, I'll put this one in brackets, x plus, and then this one is just going to be x to the 1/2, and then that to the 1/2. Did I do that right? Okay, so square root of x plus square root of x plus square root of x. Okay, that looks good. Doesn't hurt to be careful. So then y prime will be 1/2 all of that stuff to the negative 1/2, so x plus x to the 1/2 to the 1/2 to the negative 1/2 times the derivative of the next layer in. So we just worked on the outside part. An expression raised to the 1/2 becomes 1/2 that expression raised to the negative 1/2 times the derivative of the inside. Derivative of x plus this stuff is going to be 1 plus the derivative of this stuff is yet another chain rule, so that's going to be 1/2 x plus x to the 1/2 to the negative 1/2, and then multiply this by, and I guess I'll switch colors here, and then multiply this by the derivative of the inside. The derivative of x plus x to the 1/2 is going to be 1 plus derivative of x to the 1/2 is 1/2 x to the negative 1/2. And of course we could rewrite this using the radical symbol if we wanted to, but I think I'm going to pass on that. Okay, so there's some chain rule examples. Let's move on to, let's see, do we want to do implicit differentiation? Okay, sure, let's do an implicit differentiation example before going to related rates. I mean, we're going to be doing implicit differentiation and related rates anyway, but just to get the gist of it, in case anyone watching this hasn't done implicit differentiation in a while. Let's do... How about this one? This one should be one of the simpler examples. Y cosine of x. equals x squared plus y squared. Okay, so to differentiate this implicitly, we've got a product rule over here, y times cosine of x, and over here is just ordinary differentiation. I think I'll do the right-hand side first since it's easier. Derivative of x squared with respect to x is 2x. Derivative of y squared with respect to x is 2y times dy dx. I know some students prefer to just write y prime because it's quicker. I like writing dy dx because y prime looks like y to the 1, and it's easy to confuse yourself and end up multiplying it, which is no good. If you write 2y y prime and mistake it for 2y y to the 1, you might turn it into 2y squared, which would be horribly wrong. Anyway, y times cosine of x, so that's going to be a product rule, f prime g plus g prime f. So derivative of y is 1 dy dx times g, so that's cosine of x, plus g prime f. G prime, derivative of cosine, is going to be negative sine, times f, which is going to be y, so I guess I'm running out of space, I'll just squeeze it in there. And yeah, let's rewrite this. So we've got dy dx times cosine of x. Effectively, that's going to be minus y sine of x equals 2x plus 2y dy dx. Okay, I was able to fit it. Okay, we want to get all the dy dx terms by themselves, so let's go ahead and do that. I'm going to add y sine of x over to the right-hand side and subtract 2y dy dx over to the left. So we get, and I guess I'll write it here, we get dy dx cosine of x that's going to be minus 2y dy dx equals 2x plus y sine of x. Okay, factor out dy dx. That leaves us with dy dx times the quantity of cosine of x minus 2y equals 2x plus y sine of x. And now all we have to do to get dy dx is divide. So dy dx equals, let's see here, we've got 2x plus y sine of x over cosine of x minus 2y. Okay, that's all good and dandy, but some students get confused when they are further asked to obtain a second derivative implicitly. That's not a question that's asked very often, so I understand the confusion, but it's not too hard to do. Let's grab a new sheet and work that out. How would we get the second derivative? So I'm going to copy what we got for our first derivative, dy dx equals 2x plus y sine of x over cosine x minus 2y and if we want to get the second derivative, we just take the derivative of the derivative. So to get our second derivative, differentiate with respect to x again, and we would have let's see, second derivative of y. You're probably used to seeing it written more like this, but it's the same exact thing. Equals, so this is going to be a quotient rule. I'm going to go ahead and start with the bottom squared. That's just the way I like to do things. If you prefer doing it numerator first, that's fine. F prime g minus g prime f. So, derivative of the top times the bottom. Well, I'll just write the bottom first then, and then figure out the derivative part of it. So, times the derivative of 2x plus y sine of x. Derivative of 2x is 2, plus the derivative of y sine of x. That is going to be a product rule, f prime g plus g prime f. So that's going to be derivative of y, which is just 1 dy dx, times g, which is sine of x, plus g prime f, so derivative of sine of x times y, so that's negative cosine of x times y. And I don't know if I'm going to have enough space for all this, but we'll see. Minus, so that was f prime g. Oh, hold on, let me check this message I got real quick. Okay, I'll deal with that later. Anyway, where was I? So we did f prime g, or at least the way I wrote it, g times f prime, minus g prime f, minus the derivative of the bottom times the top. Okay, so the top is just going to be 2x plus y sine of x, and then the derivative of the bottom times the derivative of the bottom, so times negative sine of x. Oh, wait a minute. Did I do something wrong earlier? We'll go back to that. Negative sine of x and then minus 2y. Derivative of negative 2y is negative 2 dy dx. And yeah, I should have planned better and written smaller or something. But let me go back to this. So this was the derivative of the top. Specifically, this part right here was a product rule for y sine of x. Derivative of sine of x is positive cosine of x. Okay, I was thinking in terms of integrals. Glad I caught that. Is there anything else here? Now I'm second guessing myself on this part. Top times derivative of the bottom, negative sine of x, minus 2 dy dx. Yeah, that looks good. Okay, and what do we do with these dy dx's now? Well, we know what dy dx is. This is dy dx, so just plug that in. And yes, this is going to turn into a super complicated expression. Maybe this wasn't the best example to use for a second derivative, but, you know, if you can understand this, then you'll probably be good with whatever they might throw at you during the exam. So, one last rewrite. Second derivative is equal to, oh boy, cosine of x minus 2y quantity squared. That's the easy part. Then we've got, I'm not even going to bother trying to simplify this. I'm just going to sub in the dy dx and leave this expression as is, if I can even fit it all in here. Maybe I should write smaller just to be on the safe side. 2x plus y sine of x over cosine of x minus 2y times sine of x plus, that's just going to be y cosine of x. So much for writing smaller. Bad habits. Minus, can I even fit all that in there? 2x plus y sine of x times negative sine of x minus 2 dy dx. Yeah, there's no way I'm fitting all that in there. Maybe if I try with a pen, since it's, you know, a thinner stroke, I might actually be able to fit it in there. So dy dx is 2x plus y sine of x. Yeah, that doesn't really fit, does it? Over cosine of x minus 2y. And I don't even have enough room left to close the parentheses, but maybe if I use some of the other papers from underneath. Yeah, there you go. That's as good as I can get it. Well, I can probably do better, but it's not worth our time. Okay, so that's first and second derivatives through implicit differentiation. Let's move on to related rates of change. What shall I do for related rates of change? We've got quite a few options. We've got shadow problems, cone problems, motion problems, etc., etc. Okay, let's do a shadow problem. So, number 16 in my book says, a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? I'll read it again. A spotlight on the ground shines on a wall 12 meters away. So there's our wall. There's 12 meters. And we've got a spotlight here. If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second. So they're 2 meters tall, and they are walking away at 1.6 meters per second. How fast is the length of his shadow on the building decreasing when he is 4 meters from the building? How fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Oh, wait, I misread. The spotlight is on the ground. Well, I didn't misread, I misinterpreted. So the spotlight isn't a lamp post. The light is shining from here. Hold on, let me do that in a different color. Okay, so that's where our spotlight is. Okay, that makes sense. And then, so it looks like, yeah, that would be the length of the shadow. And so it's asking how fast is the length of his shadow on the building decreasing when he is 4 meters from the building. So the common mistake that a lot of students make for these problems is that they will try to plug in the numbers they were given before differentiating. Always differentiate before plugging in your numbers. Of course, our question now is what to differentiate. So there's a relationship between the man's distance from the building and the length of his shadow. Let's call this x, and let's call this y for simplicity's sake. I don't know why I drew that again. I already had that green bar, but oh well. Let's see, so if we call that x and we call that y, then 1.6 meters per second, that's the rate of change of x, or rather, it's the rate of change of 12 minus x. Well, actually, no. We could do it as a rate of change of x, because if you're moving 1.6 meters per second to the right, that's basically the same as x decreasing by 1.6 meters every second. Okay, yeah, we can do that. So I can say dx dt, at least the way I've defined x, is equal to negative 1.6 meters per second. Alternatively, you could have made this x, in which case dx dt would be positive 1.6, and then this would just have been 12 minus x if you had done it that way. But, you know, at that point it's kind of your choice. As long as you stay consistent with your choices, you should end up with the same result. So let me see. We got dx dt negative 1.6 meters per second. We want to find the rate of change of the length, so we want to find dy dt, the rate of change of the length of the shadow. That's our target. Got another message. Sorry for all these unexpected interruptions today. Oh, okay. Yeah, I'll handle that later as well. Anyway, where was I? So dx dt negative 1.6 meters per second, dy dt we need to figure out. In order to get dy dt, we need to establish a relationship between x and y. Okay, so I guess we can do similar triangles then. If I take this and call it 12 minus x, then I can say the ratio between 2 and 12 minus x is equal to the ratio between y and x. So I can say 2 over 12 minus x equals y over x, and I might want to rearrange this a bit. Let's go ahead and cross multiply. So we get y times 12 minus x is equal to 2x. Do I want to distribute the y or divide the 12 minus x? I think I'd rather distribute the y. Yeah, that's the way I'm going to do it, though you could do it the other way if you really wanted to. So 2x is equal to 12y minus yx. Okay, if we differentiate this implicitly, then we get, we're differentiating with respect to t here, so derivative of 2x with respect to t is 2 times dx dt equals derivative of 12y is 12 dy dt, and then derivative of yx, should have left more space for this. I should really get into the habit of starting my equations on the left end of the page. Anyway, derivative of yx, so it's going to be derivative of y times x plus derivative of x times y, so that's dy dt times x plus dx dt times y. Barely able to fit that in there. Okay, maybe this wasn't the smartest way to go about this. Maybe dividing by 12 minus x would have been the better choice after all. But I'm going to gather my dx dt terms and my dy dt terms. Actually, no, I just have to gather the dy dt terms. I don't have to worry about the dx dt because I'm going to be plugging that in as negative 1.6 anyway. Yeah, so just get the dy dt terms by themselves, or at least grouped together. So let me actually start on the left hand side and take my own advice for a change. 2 dx dt equals 12 dy dt. Distributing the minus sign, we get minus. I'm just going to rewrite that as x dy dt, and also minus y dx dt. Y dx dt. Okay, so putting these together, I would have 2, well, I'll also add y dx dt over to the left-hand side, why not? So 2 dx dt plus y dx dt is 2 plus y dx dt equals 12 dy dt minus x dy dt is 12 minus x dy dt. Dy dt is what we're trying to solve for. So now is the time to plug in our numbers. We need to plug in dx dt is negative 1.6 at the moment when the man is standing 4 meters from the building. So at the moment where x equals 4. But we also have to plug in a y here, so what is y when x equals 4? Let's see, going back to this, if I substitute 4 for x, 2 over 12 minus 4 is 2 over 8, equals y over 4. So that's going to be 1/4 times 4, y equals 1. When x equals 4 and y equals 1, dy dt is going to be 2 plus 1 times negative 1.6 equals 12 minus 4 dy dt. Let's see, 3 times negative 1.6 is negative 4.8, and then over here we've got an 8. Negative 4.8 divided by 8 should be negative 0.6. So we get negative 0.6 equals dy dt. And it should make sense that it's coming out negative. The further you stand from the light, the shorter the shadow would be. If I were to draw the man again, just further along, closer to the wall, like say here, then the spotlight goes over his head at a smaller angle, resulting in a shorter shadow. Okay, so there was one related rates problem. Let's do another one. Why not do one that you're not used to seeing? So this one is marked in red, which implies that it should be a bit more challenging. Let me read it before I start it. If it's too esoteric, then it's not worth it. let's see. Temperature, blah, blah, blah. Suppose that at a certain instant. It doesn't seem too far out there. Okay, let's give it a whirl. So it says, Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure P and volume V satisfy the equation PV equals C, where C is a constant. Suppose that at a certain instant, the volume is 600 cubic centimeters. So at some point, and I can see this purple marker is fading, at some point V is equal to 600 cubic centimeters. And the pressure is 150 kilopascals. 150 kilopascals. And the pressure is increasing at a rate of 20 kilopascals per minute. So we have dP dt is constant, and it is equal to 20 kilopascals per minute. It's an increase, so that's positive 20 kilopascals per minute. At what rate is the volume decreasing at this instant? So their question, what is dV dt? All right. So those of you who know their chemistry might be worried a little bit about how the units are working out. You don't need to worry. The units will just come out as what they need to be here. They don't expect you to have the chemistry background knowledge for this problem, and you don't actually need it. Where do I want to start? Well, I guess I should just start by differentiating this. They already gave us our equation. All we have to do is take the derivative with respect to time. So we've got a product rule on this side, and this is a constant. Derivative of a constant is always 0, so that takes care of that end. Pressure times volume. So derivative of pressure times volume plus derivative of volume times pressure. Simple product rule. dP dt times V plus dV dt times P. And I guess, just to make it look nicer, I'll move the equals 0 closer. Alright. That's all we need, so the rest is just plugging in the numbers. Let's see, we've got a volume of 600. Yeah, I don't know why this one was marked in red then. dP dt is positive 20. Usually in textbooks, when a problem is marked in red, that indicates that the problem is supposed to be harder. And maybe it is harder in the sense that it's just different from what you're used to seeing. But that's one of the more important skills that any good math student needs to work on developing, being able to apply your math knowledge to a variety of unfamiliar scenarios. dV dt is what we're solving for, and the pressure at that moment is 150 kilopascals, and that all equals 0. So let's see, 20 times 600 is equal to negative 150 dV dt. So I'm actually going to leave it as 20 times 600. equals negative 150 dV dt, and divide by negative 150. If I multiplied it, then I would have gotten, what, 12,000, and then you would have had to try and divide that by negative 150, and a lot of people would just give up and use the calculator at that point, but in fact you don't need it, because it's easy enough without a calculator to divide 600 by 150. First of all, you can reduce them by a factor of 10, and then 60 over 15, any good calculus student would know that that's just going to be 4. So we've got 20 times 60 over negative 15 is negative 4 equals dV dt. So dV dt is equal to negative 80, and that's going to be cubic centimeters per minute. And if you don't trust that that's going to be that those are the correct units, we can actually follow along and see that the units do actually work out to be cubic centimeters per minute. We had, and I guess this might be extra at this point, especially for the calculus students. Usually you don't concern yourselves with units, but just in case, being able to follow along the units isn't too hard. You've got 20 was in kilopascals per minute, so we did kilopascals per minute. Actually, let me do it over here with this equation. So we had kilopascals per minute times the 600, that was cubic centimeters, times cubic centimeters, equals the 150 was in kilopascals, times whatever units dV dt was supposed to have. Well, you can divide both sides by kilopascals, and the kilopascals cancel out, and all you're left with is cubic centimeters over minutes. So that's what we're supposed to get here. Pretty simple stuff. Okay, I think that is enough of related rates. Where to go next? How about everybody's favorite type of problem, maximums and minimums, and concavity and whatnot? Let me see. I vaguely remember a really good one that I made up one time. I wonder if I actually still have it on my phone. Let me see if I can dig it up. And first of all, let me figure out which phone it's on. Is it anywhere here? Doesn't look like it. Maybe it's on the other phone then. Give me a minute here. Okay, I think I have found it. So let's give this one a whirl. Let's just do one mega problem asking for pretty much everything. So we've got, let me see, how do I want to orient this so I can actually read it? Okay, so we have f of x equals 1/4 x to the 4th minus 2/3 x cubed minus 15/2 x squared plus 3 And I guess when I originally wrote this problem, I didn't define a fixed interval, so this is just going to be on the interval from negative infinity to infinity, unless I decide to change that later to make the problem more interesting. But yeah, there we go. So my question is, find pretty much everything. Find everything. So find, let's see, intervals where f of x is increasing. Actually, instead of writing that every single time, intervals where f of x is, okay, part A, increasing, part B, decreasing, part C, let me see here, part C, I guess concave up, part D, concave down. Yeah, not gonna risk it. I don't think I could fit it in there, not with the size of my handwriting. Concave up, concave down, and then what else do we want to find? Also find local, I guess this would be part E, local or absolute. That's not how you spell absolute. Maximums. And then part F, local or absolute minimums. Local or absolute minimums. I mean, technically it should be minima and maxima. That would be the correct plural, but, you know, I don't expect everybody to know that, so I want to avoid confusing too many people for now. And then part G, find inflection points, if they exist. So yeah, find everything. And I guess I'll add a part H, sketch the curve. Part H, sketch the curve. Well, should I? We'll see. We'll see when we get to it. So, yeah, let's just go ahead and start taking derivatives. To find intervals where f of x is increasing, we want to take the first derivative. So the way I like to do it, and maybe your teacher does it differently, but the way I like to do it is by setting up a number line. So let's get f prime of x first, and for those of you that are unfamiliar with the number line method, we'll get to that when we get to that. So f prime of x equals derivative of 1/4 x to the 4th is just going to be x cubed minus derivative of 2/3 x cubed is 2x squared minus, that's going to be 15x plus nothing. Okay, so that's f prime of x, which I can factor, and we're going to want to factor it to figure out where f is increasing or decreasing. we need to find where f is positive or negative, and the best way to find out where it's positive or negative is to find out where it's neither positive nor negative. In other words, to find out where it is 0. So factoring out an x, we get x times x squared minus 2x minus 15, which further factors into, let's see, negative 15, so I would get that from negative 5 and 3, it looks like. Alright, so those are the factors of f prime of x. Now then, to draw my number line for f prime of x. So basically, for those of you who haven't seen this number line method before, what I do is I just create a number line and mark relevant points on the number line, specifically in this case where I know f prime of x is going to be 0. So where would that be? At 0, at 5, and at negative 3. So I'm going to mark negative 3. And I usually don't draw this to scale, so if you see that my spacing between negative 3 and 0, what's the phrase I'm looking for? Well, if I end up drawing, like, maybe not in this one, but later, if I end up drawing like my 5 at the same distance from 0 as negative 3, just don't take it to mean that my drawing is to scale. That's all. I usually don't think about scaling my number lines because usually I do these problems in a bit of a hurry. So yeah, those are the 3 points where we get zeros, and I just like to, write a big 0 there to remind myself that those are places where I get zeros. If I got a derivative being undefined, if there were points where the derivative was undefined, I would also mark them on the number line. I would mark them with vertical dotted lines, like a vertical asymptote. And if it's outside of the interval or outside of the domain, usually I'll mark the point where the domain cuts off and just kind of scribble out that part of the number line. But you can do whatever you want, whatever makes sense to you when it comes to these number lines. Okay, so I know where the function is 0, or where the derivative is 0. So everywhere else it must be either positive or negative. And because this derivative is a polynomial and all polynomials are continuous everywhere, I can say that the only way for the function, or for the derivative, I should say, to change from negative to positive or from positive to negative is to go through 0. That's what we know from the intermediate value theorem. You can't go from negative to positive or positive to negative continuously without going through 0. So I shouldn't expect a change from positive to negative before hitting negative 3, 0, or 5. Those are the only points where I expect the sign to change. So if I pick a random number here, less than negative 3, and plug it into f prime of x, if I get a positive for that number, I get a positive for all numbers before negative 3, because there's no way to change the sign before hitting a 0. Anyway, let's work it out and see what we actually get. So if I pick, let's say, negative 4. Okay, so we'd have negative 4 times negative 4 minus 5 is also negative, so I've got a negative times a negative so far. And then negative 4 plus 3, that's also negative. 3 negatives, when multiplied, results in a negative. So I know if it's true for negative 4, it's true for any number less than negative 3. Can't switch to positive before passing through one of the roots. Before passing through one of the zeros, no change in signs can happen. Okay, but just because we do hit a 0 doesn't mean that a change in signs is guaranteed to happen. It will often be the case, but not always. So let's see what we get between -3 and 0. Let's test, for example, x equals -1. -1 is negative, -1 minus 5 is negative, -1 plus 3 is positive. Negative times positive is positive. So everything between -3 and 0 will give us f prime of x is positive. Between 0 and 5, let's pick 1. 1 is positive, 1 minus 5 is negative, 1 plus 3 is positive. So positive times positive is negative. Alright, then pick something past 5, let's say 6. 6 is positive, times 6 minus 5 is positive, times 6 plus 3 is positive. So positive times positive is positive. So we have now determined that f prime of x is negative for x less than -3 and for x between 0 and 5, and positive everywhere else. So now we can actually do parts A and B pretty easily. We're increasing from -infinity to -3, not including the -3, because at -3 your derivative is 0. It's neither increasing nor decreasing. Also, we are decreasing between 0 and 5. Wait. Did I? Oh. Okay, so I guess we're doing decreasing first then. Decreasing from -infinity to -3 and from 0 to 5. Okay, and we're increasing from -3 to 0 and from 5 to infinity. 5 to infinity. Alright, there we go. That takes care of parts A and B. Where are we? Concave up versus concave down. So for that, we want to take the second derivative. Let's do this one in purple and do it on another sheet. So f double prime of x is equal to, well, if f prime of x is anything to go by, then we've got 3x squared minus 4x minus 15. 3x squared minus 4x minus 15. Which might be factorable. Well, we'll see. So 3x and x. 3 times -15 is -45. -9 times 5, which -9 times 5, that would give us -4. So to get -9, I would need to multiply 3 by -3. Okay. And what was that again? That was 5. Okay, testing, so 5x minus 9x is -4x. Okay, that does it. So then, for our number line of f double prime of x, where are the zeros or points where the second derivative doesn't exist? Well, the second derivative doesn't have any points where it doesn't exist, so all we have are zeros, and we don't have any endpoints because it was on an open interval. 3x plus 5, so that would give us -5/3 is one of the zeros, and then x minus 3. So at x equals 3, we have another of our zeros. And now we just test numbers around those zeros to see what we get. So let's test a number less than negative 5/3. How about negative 6/3, which would be negative 2? 3 times negative 2 is negative 6, plus 5 is negative, and then negative 2 minus 3 is also negative, so negative times negative is positive. If I plug in a number less than negative 5/3, I end up with positives. Okay, what about between negative 5/3 and 3? So let's pick 0. 0 is definitely between them. 3 times 0 plus 5 is positive. 0 minus 3 is negative. Positive times negative is negative. And then greater than 3, so let's do 4. 3 times 4 plus 5, that's positive. 4 minus 3, that's positive. Positive times positive is positive. And there we go, there's f double prime of x. So we can answer parts C and D now. Concave up, I'll just abbreviate it C up, from negative infinity to negative 5/3, and from 3 to positive infinity. Concave down from negative 5/3 to 3. Alright, and that takes care of that. What else did we have here? So that takes care of concavity. Local or absolute maximums. Local or absolute maximums. So we've got we'll have local minimums and maximums wherever we see a change in the sign of the first derivative. At least that's where we expect to find them. Or, well, at your critical points, that's where you want to check. So points where the first derivative is 0 or undefined, or at your endpoints. We don't have any endpoints in this case, but yeah, that's what you want to check for. So maximums occur when you switch from increasing to decreasing, such as over here, from positive first derivative to negative first derivative. You can imagine a graph going up between negative 3 and 0, and then it turns around at some point and starts going down. That means you've hit some sort of peak, some sort of maximum value, even if it's not the highest value on the graph. And I think that's the only point we have that could be qualified as a maximum. So only local maximum we have is at 0. And I suppose, depending on how the question is phrased, you may also want to calculate the y value that goes with it. So in this case, we've got a local maximum at 0. So local maximum at 0. But what is the local maximum value? So if they ask for the local maximum value, then you actually have to plug in the 0 into the original function, so that's just going to give us 3. So I guess I could also say it's at 0, 3. And if you're not sure if they're asking for both the x and y value, then I would just go ahead and give both the x and y value just to be on the safe side. But I guess it depends on how the problem is phrased and whether or not you can get away with it. We'll test whether or not it's an absolute maximum later. As for our minimum values, so those occur whenever you switch from going down to going up. So whenever you switch from negative first derivative to positive first derivative, and that occurs twice, it looks like. Going down, then turning up, we've got a minimum at negative 3. Going down, then turning up, we've got a minimum at 5. So we've got minimum at x equals negative 3 and at x equals 5. What are the points associated with those? Do I actually want to calculate them? Sure, why not? Let's see, so we've got 1/4 times, I'll just use a calculator to speed things up, 1/4 times negative 3 to the 4th, which I guess once you raise it to the 4th is positive 3 to the 4th. 1/4 times negative 3 in parentheses to the 4th minus 2/3. Let's see, parentheses, negative 3, close parentheses and cube, minus 15/2 times negative 3, close parentheses and square, plus 3. And I'm getting, it simplifies to negative 105 over 4. So we've got negative 3, comma, negative 105 over 4. And then the other minimum is at 5, comma, let's see, so I'm just going to copy the formula from here and replace all my negative 3's with 5's. And that gives me negative 1339 over 12. 5, comma, negative 1339 over 12. Which of these is lower? Well, negative 105 over 4 is almost negative 100 over 4, which would have been negative 25-ish. And then negative 1339 over 12, let's pretend it was negative 1200 over 12. Negative 1200 over 12 would be negative 100, so it looks like something around negative 100 versus something around negative 25. This one is the lower minimum and might be the absolute minimum, but it depends on the shape of our graph. Pre-calculus was all about getting you to understand the shapes of graphs, among other things. This is a 4th degree polynomial with a positive leading coefficient. Okay, so it's even degree. And it's got a positive leading coefficient. For even degree polynomials, if you've got a positive leading coefficient, then eventually the end behavior is that the left end and right end, they go in the same direction because it's an even degree, and they go up because the leading coefficient is positive. And you might get something that maybe looks like this, for example. Okay, so we definitely have an absolute minimum then, but we don't have an absolute maximum because the maximum, I guess, is infinity. You can go up forever in either direction, so there's no clear winner there. Infinity is not a number. Infinity is how many numbers there are. That's a quote taken straight from Vsauce. I think it was on his video about the Banach-Tarski paradox, in case you want to look at it later. Or right now, in case you're bored with what I'm doing. Okay, so that takes care of maximums and minimums, and it looks like we don't have an absolute maximum, but we do have an absolute minimum at 5, negative 1339 over 12. And inflection points. So we've taken care of maximums and minimums. Inflection points. Inflection points occur wherever the second derivative is either 0 or undefined. At least that's where they might occur. But the true final test is whether or not there's a change in the sign. So we've got positive to negative and negative to positive. We have two sign changes, one at negative 5/3 and one at 3. So we do have two inflection points here. We do have two inflection points. And I guess I'll just write it over here. Let me wall this stuff off just to be on the safe side. So inflection points at x equals, where did I put it? Oh, there it is. At x equals negative 5/3 and at x equals 3. So negative 5/3 comma something and 3 comma something. You know how to plug negative 5/3 and 3 into the main function to get what that value ought to be, so I'm not going to waste your time with that. And then sketching the curve. Do we actually want to sketch this curve? Well, I'll write a different problem on curve sketching. Or maybe I can find one in my book. But yeah, that takes care of extreme value theorem and the first and second derivative tests. Where do we want to go from here? Well, I suppose I should do an example with a closed interval before we move on to a different topic. How about looking for a decent one. I'm liking the look of what's numbered 47 in my book. So it looks like it gives us, should I do it on an entirely new sheet? Nah. So we've got f of x equals 2x cubed minus 3x squared minus 12x plus 1, and we've got the closed interval negative 2 to 3. Unless you have vertical asymptotes, whenever you've got a closed interval, you are guaranteed to have an absolute minimum and absolute maximum value. Only exception is if you also have some vertical asymptotes. This is a polynomial, we're not going to have that. So we are guaranteed for this problem to have an absolute maximum and an absolute minimum. Okay, so let's go ahead and find them. So that's all I'm going to ask for this problem. Find all max and min values, including the absolute max and min values. The values, so we actually want to calculate the y's this time. I mean, we did that last time too, but you know. If they say find the maximum and minimum values, they mean the y value. If they want you to just find where the maximums and minimums occur, they just want the x values. You've probably heard that 100 times from your teachers, but just in case 100 wasn't sufficient, now you've heard it 101 times. Let's go ahead and differentiate. F prime of x equals 6x squared minus 6x minus 12. If we factor this, well, we can factor out a 6. And then we've got x squared minus x minus 2, which I believe can factor further into, looks like minus 2 and plus 1 will work here. Alright, and number line. At least that's the way I like to do it. If you prefer to do it in different ways, that's fine too. But yeah, find where f prime of x is equal to 0 or undefined. It's never going to be undefined since it's a polynomial. So where is it 0? It is 0 at x equals positive 2. And it is 0 at x equals negative 1. So that's where I have zeros. This time I have a limited interval, so I'm going to go ahead and draw this closing bracket at negative 2 and a closing bracket at positive 3. And just scribble out the rest of the number line. And let's sign test all of our values here. So we've got between negative 1 and negative 2. I mean, there's nothing particularly special about negative 2, so anything less than negative 1 will do. But let's say we pick negative 1.5. Okay, if x is negative 1.5, negative 1.5 minus 2 is negative. Gonna wait for that lawnmower to pass by. Okay, let's try that again. Hopefully we won't get interrupted. Spoke too soon. Ah, great. I don't even know if you can hear that lawnmower, but I am next to the window, so I'm not going to take my chances. Okay, I think they're done mowing over there. So, where was I? I lost my train of thought, thanks to that lawnmower. What were we doing? Oh, right, testing x equals negative 1.5. So, if I plug in negative 1.5 here, we've got 6 times a negative times negative 1.5. Why do I even bother? The interruptions just keep on coming. Okay, fingers crossed, hoping the lawnmower doesn't come back again. Negative 1.5 minus 2 is negative. Negative 1.5 plus 1 is negative. 6 is always positive, so positive times negative is positive. Between negative 1 and 2, we can test 0. 0 minus 2 is negative. 0 plus 1 is positive. 6 is positive. Positive times positive is negative. And then greater than 2 doesn't have to be between 2 and 3, but let's just say for the sake of argument, in case you're uncomfortable with something larger than 3, let's say we pick 2.5. 2.5 minus 2 is positive, 2.5 plus 1 is positive, times 6 is still positive, so there's that. Alright. Now then, Finding maximum and minimum values. So we also have to test the endpoints now. We also have to test the endpoints. And I guess the one way you could go about doing this is just evaluate f of negative 2, f of negative 1, f of 2, and f of 3, and compare which one's the largest and which one's the smallest, and there's your absolute maximums and minimums. I mean, we'd have to make that comparison anyway for finding the absolutes, but for finding local maximum and minimum values, you don't actually have to do that. So for the endpoints, negative 2, so starting from negative 2, the function increases. That means it started somewhere below where it ends up by the time you hit x equals negative 1. At negative 2, you started somewhere. Maybe the y value was negative there, maybe it was positive, doesn't matter. What matters is that you increased from there, which means it's lower than its neighbors. So it must be some sort of minimum value at negative 2. Maybe it's the absolute minimum, we'll find out later. Then at negative 1, so you've switched from increasing to decreasing. So that is emblematic of a maximum. So we've got a maximum over here. We'll determine whether it's absolute later. Then we went from decreasing to increasing, so that means that we've got another minimum. And then we increased towards positive 3. So we've got another endpoint at positive 3. At x equals positive 3, we have an endpoint. And you increased leading up to it, which means all the values leading up to it were less than whatever the y value was at 3. So that would mean that you've got a maximum at the right endpoint. Okay, and determining which ones are local or absolutes, compare the minimums to each other, compare the maximums to each other. So compare f of negative 2 and f of 2. Can I even fit that in here? I'll try. F of negative 2 and f of 2. What are they equal to? Let's see, negative 2 cubed is negative 8 times 2 is negative 16. And then we've got negative 16 minus 3 times 4. So negative 16 minus 12, that's negative 28 so far. Minus 12 times negative 2, so that's plus 24. Negative 28 plus 24 is negative 4, plus 1 is negative 3. And then f of 2 would be, let's see, that's going to be 16 minus 12 is 4, minus 24 is negative 20, plus 1 is negative 19. If I did my math right, then it looks like f of 2 is going to give us our absolute minimum. Okay, so the lowest low is at 2 comma negative 19, unless I made some sort of mistake calculating that. For the absolute maximum, try negative 1 versus 3. With negative 1, we've got negative 2 minus 3 is negative 5, plus 12 is 7, plus 1 is 8. So f of negative 1 is, what was it again? It was 8. 16 minus, or wait, 16, no. Negative 2 minus 3 is negative 5, plus 12 is 7, plus 1, yeah, that's 8. And then f of 3, let's see, so that's 2 times 27 is 54, minus 3 times 9, so that's minus 27 is 27. And then 27 minus 36 is going to be negative 9, plus 1 is negative 8. So it looks like the higher high is at negative 1. So our absolute maximum occurs at negative 1, 8. While 3, negative 8 is a local maximum. Okay, that takes care of that. Where is... I think they might have a problem for curve sketching here. Where can I find it? Okay, I think this might be the section that has those problems. No, it doesn't look like it. Okay, I may have to write my own. I guess I'll do that. Okay, so the type of problem I'm looking for, and maybe I just glossed over it and missed it in the book, but the type of problem I'm looking for looks something like this. It says, sketch a curve that has the following properties. Sketch a curve with the following properties. Let's say it's increasing from negative infinity to negative 2, and then from, let's say, positive 3 to 7, and then from, let's say, 10 to infinity. Decreasing everywhere else, decreasing from negative 2 to 3, it looks like, and from 7 to 10. Do I have any gaps there? No? Looking good. Okay. I have to be extra careful whenever I'm making up a problem because my regular students can tell you I have a history of trying to make up problems on the fly during the session only to have them turn out to be far more complicated because the numbers I chose randomly just don't make for a very nice problem. But I digress. So next up we've got concavity. So it's going to be concave up from negative infinity to negative 5, and from 5 to positive infinity, and concave down pretty much everywhere else, so from negative 5 to 5. So they might give you this, and they might even give you more details. They might give you like the x and y intercepts. Basically, the more detail they give you, the more detail they expect to have in your sketch. But the rule of thumb is show as much as you can about the graph, show as many features as you can based on what you know about the graph. And if there's something that they don't tell you about, then that just means you're free to assume it's whatever you want it to be. So if they don't tell you about the x and y intercepts, you can make the x and y intercepts be whatever you like them to be. And sometimes, instead of listing it out like this, sometimes what they'll do is they'll give you graphs of the first and second derivatives, and you're supposed to use that to figure out the intervals of increasing, decreasing, and upward and downward concavity. So that's a variation on this problem, but it's still the same thing. So if you're one of my regular students, you've probably heard me talk about this before. This is what I call the four strokes. The four strokes. Not an official name, but that's just what I like to call them. Or maybe it is an official name and I just happen to guess it correctly. Who knows? But these are the four strokes I've told my students on relevant occasions to make sure that they understand them. So the four strokes look like this. Let's see. And then we've got that and that. Okay, so make sure you know these four different curve shapes. Knowing these four is the key to solving problems like this. So this is an example of a portion of a graph that is increasing and concave up. Or no, concave down. Increasing, concave down. Goes up as you go to the right and is down like a frown. This over here is what it looks like if it's still increasing but concave up. Over here we've got decreasing, concave down, goes down as you go to the right and is also oriented down like a frown, and then this curves upward, so it's still decreasing but it's concave up. Make sure you know these four shapes. Commit them to memory. Well, actually, what I would say is make sure you understand them so that you don't have to memorize them. Understand those four shapes. Okay, so now what I want to do is I want to draw the number lines for the increasing, decreasing, and the concavity. So the first and second derivative number lines. You don't have to use number lines if you don't want to, but I find it helpful to have that visual. So I'll just label this the f prime number line. And I'll label this next one the f double prime number line. And this time I want to be careful with how I label my critical points. I want to make sure that they match up across both number lines. So wherever I have x equals 0 on this orange number line, that's where I want x equals 0 on the green number line to be, and vice versa. So let's see. I'll start with the orange one. So it looks like we've got -2 is a point of interest, 3 is a point of interest, 7 is a point of interest, and 10 is a point of interest. And let me plan ahead. So it looks like -5 and 5 are going to be points of interest on the green. Okay, I can make that work. So I'll put -2 over here, and I guess I'll put 3 over here, and I'll put 7 over here, and I'll put 10 over here. And then for the green number line, points of interest include -5 and 5. So I want -5 to be... Oh, yeah, I didn't... Okay, fine. -5 goes here then. And then +5 is going to be somewhere between 3 and 7. Okay, there we go. And now what I'm going to do, I guess I'll do this in pen. Well, should I do that first or do it later? I'll do it later. Let's mark the signs first. So I guess I'll do that in purple. Let's see, for f prime, from -infinity to -2 it's increasing, so that's a positive first derivative. We don't know at -2 whether we have a point where the first derivative is undefined, or if it's 0. Well, it's probably going to be 0 because I never said it was undefined at -2 for the second derivative. So yeah, it's probably a 0, but the point is we don't know what exactly we have at -2. Could be undefined or could be a derivative of 0. And I'm leaning more towards a derivative of 0, but that's getting a bit too esoteric. Between -2 and 3, it's decreasing. Between 3 and 7, it's increasing. Between 7 and 10, it's decreasing. And from 10 to infinity, it's increasing again. Okay, and then for concavity, it looks like it's concave down between -5 and 5, concave up otherwise. So negative between -5 and 5, positive everywhere else. Okay, so now what I want to do is cut this up into a bunch of sections. Where's my ruler? I mean, well, I don't really need my ruler for this. So everywhere where you have a critical point on either number line, you want to draw, I guess it doesn't have to be a dotted line, it could be a solid line if you prefer, but what I like to do is just draw a dotted line here. And yeah, now we've got, let's see, 1, 2, 3, 4, 5, 6, 7 different sections that we need to look at. So, first section we have is from -infinity to -5. Then we've got from -5 to -2, -2 to 3, 3 to 5, 5 to 7, 7 to 10, and 10 to infinity. So I'm not going to list those all out, but that's what we're looking at. So in this first region, from -infinity to -5, we've got increasing concave up. Increasing concave up. That would look like this. Then we've got increasing concave down. Between -5 and -2, we've got a positive first derivative and a negative second derivative. That would look like this, increasing concave down. Then we've got decreasing concave down, so that would look like this. Then between 3 and 5, we've got increasing concave down, so that's going to look like, let's see, increasing and concave down would look like that. Oh, well, we drew it before. Then we've got from 5 to 7. From 5 to 7, we've got increasing concave up. So that should look like that. From 7 to 10, we've got decreasing concave up. So that should look like this. This is a very weird looking graph, judging by what I've drawn so far. And then from 10 to infinity, we've got increasing concave up. So putting those pieces together, you should be able to provide a decent sketch of the curve. And there's more than one correct answer here, but, you know. Yeah, I want -5, and I want my x-axis to go all the way up to +10. So here's -5, here's +5, and there's +10. And I guess it might be worthwhile to mark all these other points. So -5, we've got 2. I'm going to try and draw this as close to scale as possible. Wait. 2, +2. What am I doing? +2 is over here. +3 is over here. Then we've got 5, 6, 7 would be around here. And 10. Okay. Let's try our best to draw this thing. So before hitting -5, it's increasing concave up, so it's going to look something like this. Then, once you hit -5, we've got an inflection point, it seems. So it's going to be increasing concave down from that point and until you hit 2, so maybe it looks something like this. And then at 2, it switches to decreasing concave down until you hit 3, which isn't too far, but my number line would have you think otherwise. As I warned earlier, my number lines are not drawn to scale. Okay, and that takes us to 3. Then we've got a switch. I guess you could draw this as a cusp, or you could just have, you know, a jump discontinuity here. Yeah, I think that's what I'm going to do. I'm just going to have a jump, and then looks like it's increasing concave down until you hit 5. Once you hit 5, it switches to increasing concave up until you reach 7. And I guess I'll make this one a cusp. Once you hit 7, it switches to decreasing concave up. And then after hitting 10, it switches to increasing concave up. And there you go. That is one of many possible graphs you could draw given this information. So remember the 4 strokes, and you should be good to go. I know that troubles a lot of students, so there it is for you. Let's see. It looks like I've got about an hour left on the clock before I have to attend to other responsibilities. Let's see what we want to do next. So we've done curve sketching. Maybe we should look at a few optimization problems. Okay, let's see which one of these piques my interest. I'm sure you've already seen your fair share of box problems, so I want to kind of avoid that. Ooh, there's an analytic geometry problem. Actually, there's a couple of them here. Maybe I should do one of those. Okay, number 19 in my book seems interesting. So it says, find the point on y equals 2x plus 3, point on y equals 2x plus 3 that is closest to the origin. That is closest to the origin. Some people will say, wait a minute, isn't that the y-intercept? No, not necessarily. Was I really about to write original? That is closest to the origin. The point on y equals 2x plus 3 that is closest to the origin. I guess we might as well draw the graph and see what we're looking at. Okay, y equals 2x plus 3, so 1, 2, 3. I guess I'll mark a 4, 5, and then there's 2 points. Let's just do it with the pen. Okay, that ought to do it. I don't know why I bothered to draw those arrows, but habits. Anyway, the point that's closest to the origin on this curve, or, well, it's not really a curve, it's a line in this case. So, the closest point, if you know your geometry, is going to be the point that makes a line perpendicular to 2x plus 3 and through the origin. So this would give us our shortest distance right here. However, even if you didn't know that, this problem is still solvable. So let's assume we didn't know that. Let's assume that our closest point is just some arbitrary point along here. Let's keep it arbitrary for now. And this orange line that I just drew represents the distance between the origin and that point. Okay, so I can draw... how do I want to do this? Actually, let me pick a different arbitrary point. Let's say I pick a point here, because that'll be easier to illustrate. Okay. You know what? Let me just redraw this whole thing all over again. It's probably going to be easier that way. So scratch all this. Let's try again. So something like this is what we're looking at. And we're trying to measure the distance of a point from the origin. Let's pick an arbitrary point, let's say over here. Okay, what is the distance of that point from the origin? What is the length of that green line? Well, we can draw a right triangle pretty easily here. So we can draw this, and we can draw this. And let's see, so this is going to have a width of x and a height of y, or a base of x and a height of y, if that's how you prefer to name them. So, by Pythagorean Theorem, we can say distance is equal to the square root of x squared plus y squared. We can say distance is equal to the square root of x squared plus y squared. And for an optimization problem, what you really want to do is write your objective function in terms of just one variable. And if the term objective function is foreign to you, that just means the function that you're trying to maximize or minimize. In this case, we're trying to maximize or minimize distance from the origin. In this case, we're trying to minimize distance from the origin, so that's our objective function. I think I want to write it in terms of x, so I want to turn this d into d of x. So d of x equals the square root of x squared plus, if I want to rewrite y in terms of x, well, we already know that. Y equals 2x plus 3. Alright, and if I FOIL that and simplify, what do I get? We get x squared plus, that'll be 4x squared plus 12x plus 9, if my math is correct. Whoops, forgot the square there. Which gives us, I guess I'll write it up here, d of x equals the square root of x squared plus 4x squared is 5x squared plus 12x plus 9. All right. Now then, if we take the derivative, d prime of x is going to be, let's see, so it's going to be 1 over 2 square root of 5x squared plus 12x plus 9 times the derivative of 5x squared plus 12x plus 9, so that's 10x plus 12. In case I lost anybody there with what I did, if you've taken the derivatives of square roots often enough, then you should know by now that the derivative of a square root, if you rewrite it as an exponent as x to the half and you do all that stuff, by the end what you end up with is 1 over 2 square root of x. So that's basically the shortcut I took. By this point in the course, if you haven't taken the derivative of square root x enough times to know that, then, well, I'm slightly concerned, but it's not the end of the world. Anyway, moving on. So that's d prime of x, and we want to maximize or minimize d of x. So d of x is going to have a maximum or minimum wherever its first derivative is 0 or undefined. We've been through this. So let's set d prime of x to 0. Let's set d prime of x equal to 0. That would mean that 10x plus 12 over 2 square root 5x squared plus 12x plus 9 would be equal to 0. And so if I multiply by 2 square root of 5x squared plus 12x plus 9, then that just gets rid of the denominator. Multiplying it by 0 doesn't change anything. The right-hand side would still be 0. And we would get 10x plus 12 equals 0. Subtract 12 and divide by 10, we would get x equals negative 1.2. Now, is that the minimum distance? No, this is where we will get the minimum distance. And how do I know it's the minimum distance that we're going to get and not the maximum distance? Because the maximum distance is infinity. This line goes on forever, and if I wanted a maximum distance, I would just pick the farthest point, but there is no farthest point. It goes on forever. So there is no maximum distance. Any critical value that we have must give us a minimum in this scenario. So at x equals negative 1.2 is where we get the minimum distance, but the question was find the point, so x and y. that is closest to the origin. And then if you want, we can actually calculate the distance too. So negative 1.2 is x. All we have to do is plug it in. Let's go ahead and do that here. Y equals 2 times negative 1.2 plus 3. That's negative 2.4 plus 3, which is 0.6. Okay, so it looks like we're going to have the closest point is at negative 1.2 comma 0.6. And if we want to calculate what that distance is, that's easily done. You could either use the d of x formula and plug in negative 1.2, or we can use the original d equals square root of x squared plus y squared, since we now know both x and y. So either route you can use to calculate what that minimum distance is if you are interested in calculating that. How about well, number 20 is similar, but I guess I'll write it for anybody who wants to try it out on their own. I'm not going to solve it. But it says find the point on y equals square root of x closest to, not the origin this time, closest to 3, 0. And I guess I'll illustrate it for you because it does slightly differ from what we did before, but not by too much. That doesn't look very straight, but we'll go with it. So y equals square root of x would look like that. And then we've got 3, 0. Okay, and if I were to pick some arbitrary point here, say that point, and I want to measure its distance. I mean, I'm assuming you already know your distance formula from geometry, but just in case, it's not too hard to reconstruct it. So this point is going to be some sort of x, y. So let's see. Then that would mean this is x and this is y. And then this distance right here would be x minus 3, and this distance right here would just be y. And from there, I think you know where this goes. Distance is equal to the square root of x minus 3 squared plus y squared. And yeah, the rest plays out similarly to what we did in the previous example. What to pick next? Okay, let's take a look at one of these. 27 says, find the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius r. So, isosceles triangle of largest area, maximum area. I don't know why I spelled area with a capital A, but isosceles triangle of maximum area that can be inscribed. That can be inscribed inscribed in a circle of radius r. In a circle of radius r. Okay, let's go ahead and draw what we're looking at. Always good to start with a drawing when it comes to these optimization problems. So we've got a circle of radius r. And inside it, we have an isosceles triangle. I'm wondering if it would also end up being an equilateral triangle. I'm not going to assume that, but I have a hunch that's what it's going to turn out to be. But for now, I'll draw it, not equilateral, just so that I don't mistakenly assume that it is. And there we go. So there's an isosceles triangle inscribed inside of a circle of radius r, and we want to maximize its area. So coming up with a formula is going to be a bit of a challenge here, but let's see what we can figure out. Well, I know this is r, and this is r, and this is r. I'm going to have to stare at this for a few minutes. We know that area of a triangle is 1/2 base times height. So I want to rewrite the base and height in terms of r somehow. And I guess the key to that is figuring out this right here. I don't think we can assume that the radius is an angle bisector, at least not for the base angles. I don't believe we're allowed to assume that, because that would mean we're assuming it's an equilateral triangle, which we already said we're not assuming. But can I still come up with an expression for this? Let's see, maybe if I draw it again. Is there anything I can see in this that I couldn't see with those red lines in the way? Unless this is depending on some sort of relationship from geometry that I'm forgetting, which I kind of doubt. I might just be missing something here. Well, I'll think about it for a few more minutes, and if I can't come up with anything, we'll just skip it, and maybe I'll do like a video later once I've figured it out. But I'll give it a couple more minutes of thought. So I know that since these radii are equal, I know that this, well, I'll use a double line for those, that creates 3 more isosceles triangles. Does that help us in any way? Law of cosines, maybe? Yeah, there's something I'm missing with this. I was expecting to be able to figure it out on the spot, but it doesn't look like that's going to happen. So I'll give this some more thought and probably post a follow-up video later. I'll probably link it in the description or something like that. Okay, let's try something different. How about... a right circular cylinder is inscribed in a sphere of radius r. Find the largest possible volume of such a cylinder. So we've got largest volume, so maximize volume. Max volume of cylinder inscribed in a sphere of radius r, I think is what they said. Yeah. Sphere of radius r. Okay. So let's go ahead and start with a drawing. So we've got ourselves a sphere, which I didn't draw too well at the top there, and inside of our sphere is an inscribed cylinder. Let's say there. Okay, and we want to maximize the volume of such a cylinder. Okay, well, one thing I do know, I guess let's label the height of this cylinder as being h. Let's label the height of the cylinder as being h. And let's see, we've got, I know this right here is equal to 1 radius. And it's related to half the height. It's related to half the height, so it's related to 1/2 h. And I guess I can define this inner radius, the radius of the cylinder itself. Let's call that big R. So I know at the very least that I have the following relationship. I know by the Pythagorean Theorem that little r squared is equal to big R squared plus the square of 1/2 h, which is the same as 1/4 h squared. But where do we go from there? If I want to... well, I guess what I want to do is let one of these, r or h, be my variable. Yeah. So let's say big R is my variable, and then the relationship that relates them sounds kind of redundant, but if I wanted to solve for h in terms of big R, so I would say 1/4 h squared is equal to little r squared minus big R squared, which means that h squared is 4 little r squared minus 4 big R squared, which means h is equal to the square root of that. So, well, if I factor out the 4, square root of 4 is 2. So 2 square root of little r squared minus big R squared, where little r is a constant. Okay, so in that case we can go ahead and set up the volume formula. Volume of the cylinder as a function of big R is going to be what? So volume of a cylinder in general is going to be pi r squared h, but if I rewrite the h in terms of big R, then that's going to be pi big R squared times the square root, or no, times 2 times the square root of little r squared minus big R squared. Okay. And then from there, differentiate and set your derivative equal to 0. So v prime of big R is equal to, this is a product rule, so we've got derivative of the first times the second, so that's just going to be 4 pi big R times the square root of little r squared minus big R squared, plus derivative of the second times the first, so 2 pi big R squared times the derivative of that square root, which is going to be 1/2 times the square root of little r squared minus big R squared, times the derivative of little r squared minus big R squared. Little r squared is a constant, minus derivative of big R squared, so that's -2 big R. Okay, there we go. And then I want to set that equal to 0. So I want to set that equal to 0 to find my optimum value. If I multiply everything by square root of little r squared minus big R squared, what will that accomplish? I would get 4 pi big R times, well, if I multiply that by itself, I just get rid of the square root, plus the 2's over here cancel, and then multiplying by square root of little r squared minus big R squared just gets rid of the denominator, and then pi big R squared times negative 2 big R is going to be negative 2 pi big R cubed. Okay, and on the right-hand side it would still be 0, even if you multiply it by anything. Alright, and then we can... well, I guess we can distribute 4 pi big R, and it looks like I need to continue this on another sheet. So we've got... how do I want to do this? Okay, let's do it like this. I'll move this up. And let's see, so 4 pi big R times little r squared minus 4 pi, that's going to be big R cubed, minus 2 pi big R cubed equals 0. Negative 4 pi big R cubed minus 2 pi big R cubed is going to be negative 6 pi big R cubed, and I'm going to add all that over to the right hand side, so 4 pi big R little r squared equals 6 pi big R cubed. I can cancel a pi on both sides. I can cancel a big R on both sides, leaving that as big R squared. And it looks like we've got it. So big R squared, or no, 6 big R squared, so I guess I need to divide by 6 as well, so 4 over 6 is 2/3. Okay, so big R squared is going to be 2/3 little r squared. Therefore, big R has to be square root of 2/3 times little r. And plug that into your V of R, and that should give you the optimal volume. Let's go ahead and plug that in. It looks like it's going to be a rather fascinating expression. So V maximum is going to be, let's see, so it's 2 pi times big R squared, so it's 2 pi times the optimal big R is, big R squared is 2/3 little r squared, so no need to undo the square root business. Times the square root of little r squared minus big R squared, which was, again, 2/3 little r squared. 2/3 little r squared. So r squared minus 2/3, or little r squared minus 2/3 little r squared is going to be 1/3 little r squared. So our maximum volume appears to be, that's going to be 4/3 pi little r squared times the square root of 1/3 little r squared. If I grab the 1/3 little r, if I grab the r squared out of the square root, then that's just going to give me an r. So that's going to be 4/3 pi little r cubed times the square root of 1/3. So it's related to the volume of the sphere in which the cylinder is inscribed, is what I get from this. So it's equal to the volume of the sphere times a factor. In this case, it's square root 1/3 the size of the sphere in which it is inscribed. Okay, that's an interesting result. I wonder if anything I've learned from this can help me with that isosceles problem. Well, one thing I didn't even try with the isosceles problem is identify my own variable. So let's go ahead and try that. Let's say I define this as the height of my triangle and define this as my base. And let's see, what does that do for me? Does that help me in any way? I mean, it fits our area formula, 1/2 base times height, but what else can I do with it? Well, I guess this over here, this dotted purple line would be, equal to, and I don't think I can even fit it in there, but it would be equal to the height minus r. It would be equal to h minus r. And I guess from there we can actually relate the height to the base. Okay, I think I know how to do this now. Okay, let's go back to this isosceles problem. So actually, I think I want to redraw this on a new sheet. That's probably for the better. And this time I'm going to draw it extra big so that I can actually write on top of it and have it be legible. Let's draw it over here. Okay, and I guess draw your center. And let's see. Do that. Do that. And connect those. Alright, so I'm going to define this as my own variable h. I'm going to define that as h. And then that would mean this right here is h minus the radius of the circle. Yeah, that r was bothering me. It looked more like a v. Now I don't even know what it looks like. And then we'll define this as 1/2 of the base. And of course, these are congruent sides. Okay, so if I draw my radii, and I guess I'll draw one here just for good measure. What can I do here? So I can say that this right here is a right triangle. So I can apply the Pythagorean Theorem. This has a length of little r. So it looks like little r squared is equal to the square of h minus r plus the square of 1/2 the base. Okay, so little r squared equals, if I go ahead and FOIL that, might as well, then that's going to be h squared minus 2hr minus, plus r squared, plus that's just going to be 1/4 b squared. Ooh, and I can cancel r squared on both sides, leaving us with 0 equals h squared minus 2hr plus 1/4 b squared. So in this case, r is a constant, h and b are variables, and I want to either solve for b in terms of h or h in terms of b so that my area function can be a function of a single variable. It looks like it would be easier to just solve for b in terms of h. So add 2hr, subtract h squared, 2hr minus h squared equals 1/4 b squared. And then multiply everything out by 4. We've got 8hr minus 4h squared equals b squared. And just take the square root, and we've got b equals square root of 8hr minus 4h squared. I guess you could also factor the 4 out and pull it out of the square root as a 2, but maybe we'll save that for later. You know what? Fine. I'll do it now. 2 square root 2hr minus h squared. There. Okay, so then our area formula was area equals 1/2 base times height. If I want to turn it into a function of exclusively height, a of h is equal to 1/2 the base, which is 2 square root of 2hr minus h squared, times the height, which is just h. Okay, it looks like the 1/2 and the 2 cancel out. And there we go. So that's a of h. Let's find a prime of h and set it equal to 0. Okay, so that's going to be a product rule unless I move the h into the square root as an h squared. Do I want to do that? Yeah, why not? So h goes into the square root as h squared, so h squared times 2hr minus h squared is square root of 2h cubed r minus h to the 4th. Okay, that'll be a little bit easier to differentiate since it's just a chain rule without a product rule. So a prime of h is going to be derivative of a square root is 1/2 times that square root. And then because of the chain rule, times the derivative of the inside. The 2 and the r are constants. Derivative of h cubed is 3h squared, so 2 times 3, so that's going to be 6r h squared, minus derivative of h to the 4th is 4h cubed. Okay, and I suppose now we can factor out the h squared that we originally put in there, that we originally put in the square root. So we end up with, and I guess we can simplify the 6 and 2 while we're at it. Oh, and the 4, yeah, 6/2 and 4/2, yeah. So it looks like we've got 3r h squared minus 2h cubed over, the 2 has been canceled out, and then we've got square root of, if I pull out an h squared, it's just 2hr minus h squared, and we'd have an h on the outside. That h on the outside reduces with the h squared and h cubed in the numerator, giving us 3rh minus 2h squared. I get the feeling I may have just wasted my time doing that, because everything in the denominator is going to get multiplied by 0 anyway. So if we set that equal to 0, I guess I'll do that up here since we have some space. We've got 3rh minus 2h squared over the square root stuff is equal to 0. If I multiply both sides by square root of 2hr minus h squared, then we should just end up with 3rh minus 2h squared equals 0. Okay, so 3rh minus 2h squared equals 0, which means 3rh equals 2h squared. Cancel an h. And so we would want our height to be 3/2 of the radius. H would have to be 3/2 r. And that would give us our maximum area. So let's see what that maximum area would be. Well, I mean, I guess you could just plug it in. Plug it into A of h, so A of h. Let's do this on a new sheet. It's getting too crowded here. So A of h, specifically A of 3/2 r, would be, I'm just going to use that simplified square root over there. It's going to be 2 times h cubed, so 3/2 cubed, that's going to be 27 over 8 r cubed times r, so there's that, minus h to the 4th, so minus 3/2 r all to the 4th. 3 to the 4th is 81, over 2 to the 4th is 16, and then r to the 4th is just r to the 4th. Alright, that gives us, well, I see we're getting r to the 4th here as well, so there's like terms to work with. 2 and 8 reduced to 4, so it looks like we've got square root of 27/4 r to the 4th minus 81/16 r to the 4th. 27/4, if I multiply by 4 over 4, that's going to be 108 over 16. 108 over 16 r to the 4th minus 81 over 16 r to the 4th. Let's see, 108 minus 81, so minus 80, that's 28, and minus 1, that's 27. So it looks like it's the square root of 27r to the 4th, which is root 27 times, if you pull it out of the square root, it becomes r squared. Okay, and that is the maximum area. And then let's figure out whether our original intuition was right. Or, well, my original intuition. I don't want to rope you into this if you don't want to be roped into it. But let's see if my original intuition was right and that we get an equilateral triangle. So how would I test for that? Well, if it is equilateral, then that would mean this angle would have to be 30 degrees. And that would mean that h minus r over r would have to be 1/2, because sine of 30 is 1/2. Let's see if that's actually true. H minus r over r, is it equal to 1/2 in the optimal condition? In the optimal condition, h is equal to 3/2 r. So 3/2 r minus r over r. 3/2 minus 1 is 1/2. 1/2 r over r cancels the r's. So yes, it is indeed 1/2, so yeah, it is an equilateral triangle. The optimal triangle that can be, the optimal isosceles triangle that can be inscribed in a circle to maximize area would be an equilateral triangle. Okay, it looks like we might have time for a couple more problems. Let's do... why not? Let's do some U substitution problems. Let's shift gears and do some integrals. What to pick, what to pick, what to pick. I guess we'll do a couple classic ones, and then if I can find some of the more complicated ones, I'll grab those. But let's do a classic. So, integral of x times sine of x squared. Alright, best choice for you in this case would have to be x squared. U equals x squared, meaning du equals 2x dx. Now, depending on how your teacher taught you to do it, some teachers will teach you to solve for dx and then get dx equals du over 2x and substitute that in for dx here, which you can do, that's fine. But the way I do it is I just look for a 2x dx and substitute that for du. Do I have a 2x dx? Well, not quite, but I can make one, because if I multiply by 2 over 2, now I've got 2x dx. I can replace all of that with du. It leads to the same end result, but depending on which method your teacher taught you, my method might seem a bit foreign to you. I would recommend you get used to it, though, especially if you plan on doing calculus in college, because that's how your professors are going to do it. So I would recommend getting used to this method. Let's see. So that leaves a factor of 1/2, which I can just pull outside of the integral. 2x dx becomes du, and sine of x squared, so x squared just becomes u, sine of u, integrated with respect to u. Okay, the integral of sine. What is a function whose derivative is sine of u? It's very easy to get your wires crossed here. I think I did that earlier in the stream, in fact. So the integral of sine is negative cosine. We've got 1/2 negative cosine of u. You can check, because if you take the derivative of negative cosine, it will give you positive sine. And of course there's plus a constant of integration. And if we resubstitute for u, we've got, and simplify of course, we've got negative 1/2 cosine of x squared plus c. Alright, all done. That's about as basic as it gets. I want to see if I can find one of those. I think this might be one of them, but I'm not sure. I'm just kind of guessing at a glance here. We've got the integral of x squared times the square root of 2 plus x dx. Yeah, this is one of those cases. Okay, so I'm going to go with u equals 2 plus x, leading to du equals dx. Doesn't seem that interesting so far, but the extra step you have to take for a situation like this is that, yeah, you can replace the inside of the square root with u, but what about the x squared on the outside? You want to rewrite that in terms of u as well. So what we need to do here is solve for x. So if u equals 2 plus x, then x equals u minus 2, which means x squared equals u minus 2 quantity squared, which is equal to u squared minus 4u plus 4. If I did my math right. Yeah. Okay, so we can rewrite this as the integral of x squared becomes u squared minus 4u plus 4 times the square root of 2 plus x just becomes the square root of u, which I'm going to rewrite as u to the 1/2 times dx just becomes du. Alright. And distribute the u to the 1/2. Distribute the u to the 1/2. And what will we get? We'll get the integral of u squared is u to the 4/2. U to the 4/2 times u to the 1/2 is u to the 5/2. Minus 4. U times u to the 1/2 is u to the 3/2. Plus, that's just 4u to the 1/2 du. Okay, and if we go ahead and integrate using our classic power rule, we will get u to the 5/2 plus 1 is 7/2 divided by 7/2. In other words, times 2/7. Well, I'll just say divided by 7/2 for now. Minus 4. U to the, if we add 1, that becomes 5/2 over 5/2 plus 4. U to the, that's going to become u to the 3/2 over 3/2 plus a constant. And if we continue that, oh, I guess I've got some blank space here, so I might as well use it. If we continue that down here, then I guess I'll rewrite that as 2/7 u to the 7/2 minus, let's see, dividing by 5/2 is the same as multiplying by 2/5. 4 times 2/5 is 8/5, so that's minus 8/5 u to the 5/2 plus 4 times, that's going to flip to 2/3, so that's 8/3 u to the 3/2 plus c, and finally rewrite in terms of x. U is equal to 2 plus x, so this is going to become 2/7 2 plus x to the 7/2 minus 8/5 2 plus x to the 5/2 plus 8/3 2 plus x to the 3/2 plus c. There we go. Let me see if I can find one of those ones that tend to trip students up when they really shouldn't. I don't see one here, so I guess I'm just gonna have to make my own. Okay, say we had the integral of x cubed minus 4x squared plus, let's call it x to the 3/2 divided by the square root of x dx. So a problem like this tends to throw students for a loop because they tend to overthink it. They try looking for u substitutions that work and they end up with nothing, and the reason is because they didn't try a much simpler method first. What you need to realize when you see this is that the denominator is not complex. If the denominator was, square root of x plus 2x minus x squared or something like that, then yeah, you would probably want to try substitution. But in this case, the denominator is a monomial. It's only got one term, which means you can just distribute it over here. So you're just going to get, if I rewrite this, it's the same as, let's see, so square root of x is x to the 1/2, and dividing by x to the 1/2 means subtracting 1/2 from each of the exponents. So this becomes the integral of x cubed over square root of x is x to the, let's see, 6/2 minus 1/2 is 5/2, minus 4x squared is x to the 4/2. 4/2 minus 1/2 is 3/2. Whoops. X to the 3/2. And then x to the 3/2 divided by x to the 1/2. 3/2 minus 1/2 is going to be x to the 2/2, which is just x to the 1 dx. And now you can just integrate normally using the power rule. So what do we get? We get x to the 7/2 over 7/2, in other words, times 2/7, minus 4 times x to the 5/2 over 5/2, so that's times 2/5. 4 times 2/5 is 8/5, and then plus, that's just going to be 1/2 x squared plus c. And there we go. So if you see a situation like this, do not overthink it. If you've got a monomial denominator, you can simply distribute it over the terms of the numerator. If your numerator is not a polynomial, or at least some expression that looks like a polynomial, you can still have, fractional exponents or negative exponents or whatever. If it doesn't look like that, then you're probably going to have to try other things. If you've got sines and cosines and exponentials in there, you might have to use a different integration technique. Okay, and that was a brief review of basic integration along with u substitution. And I guess this is where we will have to call it quits for today. I guess we'll continue just from where we left off tomorrow, hoping everything worked out fine technology-wise. I have to see whether or not the recording actually functioned correctly. I am still new to this stuff, so this really is just a trial run. I hope I have a recording to post. But yeah, that's where it's going to end for today. So hopefully you found this to be helpful, whether you watched it live or you were watching the recording, assuming that the recording is even there. But if you are watching the recording, you already know the outcome of that. So let me just stop rambling. This has been Al the Tutor, reminding you that ignorance is not bliss. Take care, and I'll probably see you tomorrow.